Today we're going to solve the same exact problem 3 different ways. First, we're going to solve it graphically, then by component method, and then finally by trigonometric method. The easiest method is solving it graphically. Although you may not get the exact number, if you're careful enough, hopefully you're within 10% of the correct answer. First thing to keep in mind is that with graph paper, it's not always exactly to the scale that you want. For example, when you look at this graph paper over here, 1 centimeter kind of lines up, but by the time you get to around 10 centimeters, you can see there's a misalignment. In other words, this graph paper here is printed out slightly smaller than at 10 centimeters for 10 centimeters. All right, so don't rely on the graph paper itself. Instead, rely upon your scale. And in this case, we're going to use a scale of, for every 1 centimeter, that will represent, I think what a good one would be is 10 kilometers. Why did I choose 10 kilometers? Because of this value up here, 120 kilometers, which would translate into 12 centimeters. And I hope that it all can fit in here with those values given there. Knowing just approximately how it would look like, I probably want to start from somewhere down here and then traverse my way through. So my first line segment is going to be 12 centimeters long, but if you're wondering at what angle it needs to be at, well, for that you'll need a protractor. And if you don't have a protractor around, it's alright. I'll include a link in the description below where you can print out your own and cut it out, and it'll work just fine. Alright, so the first one is east 60 degrees towards the north. In other words, from east, I need to tilt 60 upwards. You'll want to line up the center of the protractor to your starting point, the 90 degrees to the top, and 0 degrees towards the right. Then we'll do a brief marking of 60 degrees up north from east. We then take out our trusty ruler and draw a line segment that is 12 centimeters long that cuts right through the 60-degree marking. And that's our first vector. Don't forget to label your first vector as delta D1. Our next vector will be 6 centimeters long. So with a graph paper, use it as an aid to make sure that you line up things perfectly horizontally or vertically. So I'm just eyeballing it here, making sure that the graph paper is parallel to the ruler. And from there, I will draw a line that's 6 centimeters long. Again, draw an arrow on top because this is a vector and it needs to include direction. And we have our delta D2 when we label it. How did I know that was towards the north? Good question. I should have included that in my diagram as well, which is a compass rose. So we'll take it that north is positive. Again, this is a scale diagram, so you need to include a scale as well as a compass rose so the reader knows where you're trying to go. The last vector is west 30 degrees towards the north. So again, I'm using the graph paper itself to try to line up my protractor to the horizon. Make sure my 90 degrees is pointing upwards approximately. And this is west 30 degrees up. Alright, so from the west, I'll tilt 30 degrees towards the north. And this line segment needs to be 4 centimeters long. Now you'll notice that 4 centimeters is all the way out there. I can start from the 10 centimeter point and just go 6 centimeters up. And there you go. That is my delta D3 with an arrow on top. To figure out my resultant displacement, I always like drawing my resultant displacement in a different color. And if you don't have a color pen, that's okay. Shift a ruler by a slight bit, and then draw another line on top. That way you have a line that is twice as thick. And this is my delta dr. What is my answer for it? Graphically? Well, you pull out your ruler, measure as necessary, and I get 186 millimeters, which translates into 186 kilometers. As for the angle, there's 2 ways of measuring the angle, either from the north or from the east. If I measure from the north, I make sure that my protractor is facing accordingly. And that looks like 6 or 7 degrees because my pen marking is too thick. I think it's on the 7. So that will be north 7 degrees towards the east. An alternate correct answer is measuring it with respect to the east-west, or the horizontal. In this case, it will be 82 degrees. So this is 186 kilometers east, 82 degrees towards the north. Either of these two answers is correct. And that's how you solve this graphically. Next, we're going to solve the same problem using the component method. What normally helps in the component method is just to draw a brief little sketch for each of these, just so you know how you're measuring each of the angles. So for the first one, we're traveling east and then 60 degrees towards the north. All right. That way we can figure out our horizontal component, which I like to draw in red, and my vertical component, which I like to draw in blue. The second one is just towards the north. That's no big deal at all. So we'll only have just a vertical component. And the last one is west 30 degrees towards the north. So from the west, tilting 30 degrees. And that way I can quickly see my horizontal component and my vertical component as a reference. These diagrams on the right, they're not necessary to draw out, but it'll definitely make your life easier when you're trying to figure out which side is positive. Speaking of positive, that's what we'll do first. We're going to deal with our delta dx dimension, and we're going to assume east as positive. So my delta dx will be equal to the sum of this component here, nothing here, and that one pointing towards the left. So my dx is equal to 120 kilometers, and here's where it helps to have a diagram. You can see that the red vector is adjacent to the 60 degrees, and that's what we're going to multiply it by the cosine of 60 degrees. The second vector is nothing, so we don't need to add it at all. I'll just put a 0 kilometers just so that we know that we took care of this one here. And the last one is not a plus, but it needs to be a negative as we're facing towards the west. So that will be negative 40 kilometers times, again, 30 degrees is adjacent to the horizontal component, so that's why you choose the cosine again. So the cosine of 30 degrees. Pull out our trusty calculator. This term over here simplifies down to 60.000 kilometers. Subtract, and the next term is 34.58 kilometers. The difference of these two works out to 25.34 kilometers, and we're done with the horizontal component for now. We then advance on to the vertical dimension. So delta dy, and we're going to take it that north is our positive direction. All right, that will be our assumption. And let's go through the math again. Delta dy is equal to this vertical component, which is opposite of 60 degrees, and that's why we're going to multiply the hypotenuse of 100 kilometers by the sine of 60 degrees. For the second vector, we just add it in, 60 kilometers. Of course, if you want to go all crazy over it, again, this is facing towards the north, and that will make it a 0 degree relationship with it, and it's also on the adjacent side of a very tall triangle. So if you really want to do the cosine of 90 degrees, you can have fun with it, and it will work out, but it's really not necessary. The last vector is also facing slightly towards the north, and that's why we're going to add one more time. We're going to add the hypotenuse times, this time around, again, this is on the opposite side, so that's why we choose sine again, the sine of 30 degrees. We go through the math of all three components, and the grand total will work out to 183.99 kilometers. So here's our horizontal component, here's our vertical component. What helps at this point is to draw out a brief sketch of what's going on. So we've traveled just a little bit towards the east and significantly towards the north. And that's why our resultant vector will look something like this. So this is our delta dr over here, our subtotal for our dx, and our subtotal for our dy. Our dr can be solved. The magnitude of our dr can be solved by using the good old Pythagorean theorem. So delta dr is equal to delta dx squared plus delta dy squared, which is equal to the square root of 25.34 kilometers bracketed squared plus open bracket 183.99 kilometers close bracket all squared. All right, don't forget to square the measure as well as the units. If all goes well, this works out to 186 kilometers. Next, by taking a look at this diagram here, we're trying to look for the angle here, and the angle is equal to the tan inverse, or the arctan, of, in this case, the opposite over the adjacent. So according to this diagram, we're going to do delta dy over delta dx. So our dy is 183.99 kilometers, and our delta dx is equal to 25.34 kilometers. Crunch through the math, and we end up with 82 degrees. So that's usually 6 out of the 7 marks. You're missing on one last mark, which is your final answer. So if this is your diagram and this is your angle, your final answer of the day is therefore your delta dr as a vector is equal to, taking a look at the givens, there are at least 3 sig figs, so 186 kilometers east, 82 degrees towards the north, and that's one of the 2 correct answers. The other correct answer is if you draw this diagram in a slightly different way. Some people like to start off with the vertical component and finish off with the horizontal component, and that's fine. You'll get the same answer, it's just that your angle bearing is relative to north as opposed to east. So according to this diagram here, your theta is equal to your tan inverse. This time around, it's not the blue over the red, but it's the red because it's opposite over the adjacent, which is your blue. Arctan is the old-fashioned way of saying tan inverse. In fact, it's the proper way of saying it, so I'll stick with the old school. So 25.34 kilometers divided by 183.99 kilometers, and you'll notice that the units always divide each other out because the arctan is always looking at a relationship of a triangle. So anytime you have a triangle with a relationship where this side is much shorter than this side, you should get a very small answer. And there are lookup tables that exist on the internet, so you can look it up for what the answer can be. Or you can pull out your calculator, and your calculator will probably spit out 8 degrees. Of course I'm going to check it out. I'm not so sure about my calculations. Well, roughly 8 degrees. It works out to 7.84 degrees. So another correct answer of my delta dr is equal to 186 kilometers. From the north, we're going to tilt 7.8 degrees towards the east. So both of these are correct. Now there's a third way of solving the same exact problem, and the third way kind of involves this diagram again. So we do need to have this diagram first before we solve using the trigonometric method. So with the previous diagram, it doesn't have to be drawn to scale like this one over here, but you do need to break it up a bit, because right now we have a quadrilateral, and the trigonometric method, as the name implies, can only be solved using triangles. So we got to break up this quadrilateral into a triangle. One of the best ways of doing that is just to break it between the first 2 vectors and the last vector. Alright, so we're going to solve for this green vector first. We'll just call it delta d1 plus 2, because it is the sum of those first two vectors. Alright, and I'll call this side C, this side A, and this side B, and then we'll use that for letter D when we eventually need that later on. Okay, So we need to solve for side C, or the length of C, but first we need to figure out the angle over here. In the problem, it states that the first vector is traveling east 60 degrees towards the north. So if you use the alternate angle theorem, or the Z pattern, that means that over here it is also 60 degrees. Another important note is that between north and west, that is 90 degrees. So that'll be our first calculation. All right, our angle C is equal to 60 degrees plus 90 degrees, which gives us a total of 150 degrees, and this is solved using the Z pattern. And, well, we're gonna plus 90 degrees from west to east. All right, so the Z pattern and the fact that west and north is 90 degrees apart from each other. All right, so now we have our angle for C. We have length of B, we have the length of A, so we can solve for D12 using good old cosine law, which is C squared, or the C is equal to the square root of A squared plus B squared minus 2AB times the cosine of C. A is D2, and D2 is 60 kilometers, so 60 kilometers squared plus D2, or sorry, B, which is 120 kilometers, minus 60 kilometers plus 120 kilometers times the cosine of 150 degrees. And this works out to 174.559 kilometers and not kilometers. Believe it or not, the proper pronunciation is kilometers. After all, you measure mass as kilograms, not kilograms. Get it? All right, back to this fun stuff now. Okay, so we're trying to look for that angle over there. So we're trying to look for angle A. All right, and after we solve for angle A, since we need to figure out the projection of this vector over here, we need to add angle A with an additional 60 degrees. So we need to use the sine law for this, and we're going to do the sine of C over C is equal to the sine of A over A. So the sine of C over C is equal to the sine of A over lowercase a. Remember, capitals for angles, lowercase for the measurements. We're solving for angle A, so angle A is equal to, we'll bring A up, so it's the sine inverse of A times sine of capital C over lowercase c. One of the issues about solving using this method is that you got to really trust that this answer up here is correct. Otherwise, it's going to throw off everything else. So A is D2, and D2 is 60 kilometers. 60 kilometers times the sine of 150 degrees, all divided by 174.559 kilometers. And this will get you the answer of 9.896 degrees. All right, so the angle of D1 plus 2 is equal to 9.896 degrees plus 60 degrees. Again, we're trying to solve for this entire span from down here all the way up there. So we got to solve for angle A, and we need to add 60 degrees to it. And this will give us a grand total of 69.896 degrees. So therefore our D12 as a vector is equal to 174.559 kilometers east, 69.896 degrees towards the north. Huh, I need more paper. I'll be back. And as you can see, the trig method, it does take quite a bit longer when you have more than two vectors. So our D12, we just solved for this right now. This is equal to 174.559 kilometers east, 69.896 degrees towards the north. And again, since this is the solution to the first two, we don't need the first two anymore, and we can just erase it. And we're left with yet another triangle. All right, where we gotta first figure out this angle over here before we move on. There's two parts of this angle. First off, D3 is facing west 30 degrees towards the north. So that's our 30 degrees. and we'll use our alternate angle theorem again, or our Z pattern, to solve for the next angle. All right, so since down here it is around 70 degrees, up there it is around 70 degrees as well. All right, so this time around our angle, we've got to be more specific now, angle DBC is equal to 30 degrees plus 69.896 degrees, which works out to 99.896 degrees. And this is using the Z pattern. And that's about it, just using the Z pattern. All right, now we know the angle here, we have the side length here, we have the side length here. We can solve for that last part. All right, so for this triangle here, we'll just use D, B, and A. All right, so side length B is equal to, now with D and A involved, it'll be D squared plus A squared minus 2AD times the cosine of angle capital B. That's equal to the square root of D is equal to 174.539 kilometers squared plus our value of A, which is our D3, which is 40.0 kilometers squared minus 2 times 40.0 kilometers times 174.559 kilometers times the cosine of 99.896 degrees. Pulling out our trusty calculator, that will give us an answer of 185.663 kilometers. Almost there. Last part is to solve for the angle all the way over here. So we have to solve for this angle here now. And that angle, again, if we ignore those, we'll just use angles A, B, and C. So this is with regards to triangle ABD, and that's actually true for both cases, even for up here. This is with regards to triangle ABD. Okay, so B we know, side B we know, angle A is what we're trying to look for, so sine of A over A is equal to sine of B over B. Solving for angle A is equal to the sine inverse of A times sine B over B. And if you're wondering how in the world are you supposed to rearrange this, it goes something like this. First we multiply the A up, so we get sine of A is equal to A times sine of B over B. All right, because you got to keep in mind that sine B kind of has brackets around it, so you can't modify that. All right, if you accidentally place A towards the end, someone might not know whether if you're supposed to multiply B and A first before doing the sine, or do you do the sine B and then multiply by A. If you write it out this way, it's guaranteed to work out beautifully. Next thing you need to do is that you have to do the opposite function of sine, which is your sine inverse. And again, whatever you do with your on the left-hand side, you must do with everybody on the right-hand side. And that's how we arrive to angle A is equal to sine inverse of A times sine of capital B over B. All right, so that's the origin story for that. We next then sub in everything we know. A is equal to 40 kilometers times the sine of 99.896 degrees divided by 185.663 kilometers, and we end up with 12.254 degrees. All right, so we have our 12.254 degrees here, plus this bigger angle of 69.896 degrees. All right, so our theta for our delta dr is equal to 12.254 degrees plus our 69.896 degrees, and then that will give us a total of 82.150 degrees. And we take a look at our original givens, 3 sig fig, 2 sig fig, we should follow suit over here as well. So our final answer is 186 kilometers east, 82 degrees towards the north, and that is our delta dr. So yet again, 3 different ways of solving the same exact problem. First graphically, then by component method, and then lastly by trigonometric method. I hope you enjoyed this episode, and for more fun adventures like this, again, continue doing your homework. That's where you'll find the most fun. Take care.